Hi everyone. Today we'll talk about an exciting new browser feature called Trusted Types and how it protects against DOM cross-site scripting. Before we move on, we'll do some introductions. Hi, I'm Jen. I work at Google. It's been over 3 years now. I work on a team for web security where we focus on deploying web security mitigations across Google's web services. So you can imagine we work with a lot of different teams. Across Google, we have about like 1 to 100 of security engineer to a product engineer. So we really care about making things work at scale.
Hey everyone, I'm Yusuf. I'm also a software engineer at Google, working on the same team as Jen. Thank you all for having us here today.
Cool. Here's a brief overview of our talk. We'll start by defining our problem, which is DOM XSS. Then we'll move on to how Trusted Types offers protection against DOM XSS. And then we'll go over how to write Trusted Types compatible code from scratch and explain how Trusted Types can be rolled out to existing applications with some sample refactorings to follow. Cross-site scripting, maybe you've heard of it, maybe you haven't. We'll give you a brief overview. This is very, very common across the web security industry, and here's some data to back it up. This is from a few years ago, but Google runs a vulnerability rewards program where we pay out security researchers when they report bugs to us. And this is like a distribution of the bugs that we've gotten. Most of them are web bugs. It makes sense, Google's a web company, but out of all those web bugs, a big portion of them were XSS, so we really had to focus on how we can remediate this at scale. So let's talk about what XSS really is and why it happens. The root cause is that user input gets mixed up with code and gets interpreted as code. Because HTML is dynamic and mixes static data with logic that should execute, as you see here, this is very prevalent in web programming. And this leads to malicious scripts getting injected into a trusted site. And in this example, here, there's a description that's supposed to be dynamic, as you can see. If this is user-controlled, we can inject the following script and get it to execute. And an XSS, when exploited, lets the attacker take control of the account of a logged-in user. This could mean many things. You can access session tokens, cookies, just take any action on behalf of the victim. So it's pretty powerful, and that's why we care a lot about remediating it. We also call this kind of like the client-side version of a remote code execution, as they share a similar concept of arbitrary code execution. And here's another format you might be used to seeing XSS. We usually pop an alert with the document domain as proof of concept that we did find an XSS vector on this domain. So let's, I guess, focus on the specific flavor of XSS that we're talking about today, which is DOM XSS. This is a client-side variant. The root cause is DOM APIs not being secure by default. If you've ever worked with JavaScript, you know it's really easy to take strings and turn them into code that executes in the browser. Some examples are inner.html, script.innerText, and various others. So here's a very simple example of how this might happen. In this code snippet that you see below, location hash is a user-controlled string. It gets assigned to inner.html, and we'll see the on-error alert statement execute. But we have a lot of like front-end frameworks that prevent using actual raw calls to inner.html. So no one codes like this anymore, right?
Except not. While frameworks tend to abstract away the complex DOM operations, this doesn't actually prevent developers from using these unsafe APIs directly. And these issues are really easy to introduce. The code might make sense and might seem safe at the time of writing it, or the developer might not be considering security since it might just be an internal app. But once this dangerous code makes its way into your code base, it becomes really hard to track down and remove. Even more so because the issue isn't just with inner.html. There's over 60 APIs that can turn strings into code, so the attack surface is really large. It's hard to keep track of all of these dangerous APIs, which makes DOM XSS very easy to introduce and very hard to detect. Calls to these APIs could be going through multiple levels of indirection. They could exist in third-party libraries we don't have control over, or be hidden in legacy code, and your app would be vulnerable without any direct action on your part. In summary, there are 3 main reasons why DOM XSS is problematic. So DOM APIs are not secure by default. Client-side JavaScript is dynamic and complex, so it's not very easy to statically analyze it. And there are a lot of organizational issues with dependencies or having a lot of developers working on the app at the same time. At Google, even though we have world-class tooling for JavaScript, where a lot of it is statically analyzed, plus world-class organizational best practices like code and security reviews, we still haven't caught all the DOM XSSs. In general, XSS is still an unsolved problem in the industry. Do we stand a chance?
And I mean, you could guess that we think we do, otherwise we wouldn't be here talking about Trusted Types, but this is essentially where Trusted Types comes in. So let's talk about how the security mitigation works and why it's been so successful for us. The main idea behind trusted types is to make security decisions explicit and auditable. To do this, trusted types will restrict access to dangerous DOM APIs that Yusuf mentioned previously. And it will require typed objects instead of plain strings to be passed into the over 60 DOM APIs. We'll talk about how to generate these typed objects in later slides, but this is the general idea behind trusted types, is to introduce a runtime type checking mechanism in the browser on top of JavaScript. So in this case, instead of using strings that represent script URLs, HTMLs, or scripts, we'll require typed objects such as trusted script URL, trusted HTML, etc. And how do we enable this? It's sent with a HTTP response header. So you just set this trusted types directive, which is required trusted types for script, in your content security policy. You can also specify a reporting endpoint to collect all the violation reports, which we'll get into later. If you remember the example from our DOM XSS slide before, we're using a plain string here with inner HTML. And if trusted types were enforced, the browser would throw an error like this, saying we need a trusted HTML object here, and it will essentially block this assignment. Then the DOM XSS attempt is unsuccessful. We want to highlight that most of the security guarantees of trusted types come from a policy, and the policy is what I mentioned previously of how we generate the actual typed object. You can think of it as a wrapper that takes in a string and returns the trusted type. And we apply this policy to strings before inserting them into the DOM sink. So the processing you do within the policy should make sure that the string won't lead to any unintended code execution, and that's where the security of trusted types essentially comes from. So in this example, we use a sanitizer from DOM Purify. We check the presence of trusted types in the JavaScript namespace for browser compatibility, because it's currently only supported on Chromium, but there's upcoming browser support from other vendors. And then we use the correct factory methods if it exists. We do know that this if block is quite verbose and long, so if you prefer using something that's compatible, DOM Purify works with trusted types off the shelf. If you just use this setting, it'll handle the policy creation and browser checking under the hood for you.
Thanks, Jen. So now that we've seen the actual API for using trusted types, how do we build a real-world application with it? We'll talk about two different approaches here. First, how to write a trusted types compatible application from scratch, and then how to refactor existing applications to be compatible, which Jen will also touch on later. One very easy way to write a trusted types compatible application is to use a framework that's already compatible. Our colleagues have done a lot of work to harden Angular and Lit, frameworks that we use internally as well. And hardening work is also pushed to open source, so all developers who use these frameworks benefit from the security improvements. But our contributions aren't only to Google-sponsored frameworks. Our friend at Meta have also worked to make React compliant with their web security strategy, and we've submitted PRs to make some React-based frameworks like Next.js work well with our suggested security frameworks as well. But as we noted before, while frameworks usually abstract away calls to dangerous APIs, there's nothing stopping developers from using these directly, which leads us into our next point, which is enforcing trusted types. A good way to ensure that no dangerous DOM APIs get used within your application is to enforce trusted types as early as possible. Trusted type violations come up in the console and are easily traceable within tests, so it's easy to make sure that any new functionality that violates trusted types is immediately detected. And this is great for integrating with your CI/CD pipelines or DevOps processes. So how can you enforce trusted types on your service? It's as simple as sending a static header through your dev server setup. Webpack is an example of a popular one that has this as a configuration. And you can also use the meta tag at the top of your HTML page to send this as a header. In addition to enforcing early, there are several tools that can help make the process much easier. The first of these is a project called Safety Web. As mentioned before, we have a huge static analysis pipeline at Google. And to build Safety Web, we took some of the most effective checks that we run on our internal linter and static analysis tooling and built it on top of ESLint. As you can see in the example here, it'll detect unsafe usages of risky APIs and alert the developer of these. And you can refactor these unsafe calls with another tool we provide, Safe Values. And this is a library designed to steer developers to make safer choices. Safe Values will prevent unsafe assignments using TypeScript type checking, unless the value is trusted, either from a trusted source or by a transformation that makes it trusted, such as sanitizing. We will talk more about the full refactoring process later. We're also actively working on a tool called Trusted Types Helper for streamlining the trusted types adoption process. One of the most time-consuming stages of trusted types enforcement is finding the source of the violations and fixing them. And this Chrome extension will create a DevTools tab that will help you demystify trusted type violations and suggest refactoring, so stay tuned. This tooling all fits into our stance at Google that many security defects in software emerge during development as a result of relying on an ecosystem that lacks sufficient support and guidance. Our goal is to contribute to building a better supported and more secure ecosystem for all developers. So in summary, we always recommend to use the frameworks that are already compatible with trusted types when you're developing web apps. Try to enforce early so that you don't have to deal with as many violations or incompatibilities, and always try to use the right tools for the job.
So what Yusuf described is kind of the straightforward path of having an application that's trusted types compatible, but in reality, we know that most of our job is going into an existing code base with realistically a lot of tech that needs to be trusted types compatible. So we'll talk about how we do that. Before we do that, we'll share some of our success stories to prove that the pain is worth it. And this could be explained by one statistic, which was 0 DOM XSS. You saw the graph I showed you before where we had a lot of reported XSS, but on applications that enforce trusted types, which is over 400 now, we had 0 reported DOM XSS so far. Many of your favorite Google products like Gemini, Photos, Docs, Gmail enforce trusted types, and they went through a very comprehensive refactoring approach to do this. And we've also invested in enforcement by default, so new products built on modern web frameworks that we have internally will have trusted types enforcement automatically, which goes into what Yusuf was saying before. And a word of warning before we do get started, making an existing web application trusted types compatible is difficult, especially because we follow a comprehensive refactoring approach with our first-party applications, but we still think it's very, very worth it, especially because it's prevented DOM XSS at such a scale. So now we'll talk at a high level about how we approach refactoring an existing complex web app to be trusted types compatible at Google, and this should apply to any other web app as well. So far, we've only talked about what happens when you enforce trusted types, but trusted types actually comes in 2 different modes. One is reporting, and the other one's enforcing. Report only will let you collect violation reports on a designated endpoint, but the browser will not block actions that violate trusted types, while enforcing will block such actions. So we can collect and triage reports without causing any feature breakages or user observable changes with reporting mode. So as we collect these violations, we'll refactor blockers to make our front-end code trusted types compliant, which we'll touch on in just a few slides. And then we'll repeat steps 2 and 3 until we're confident that there's no trusted types incompatible code in the first-party code that we ship. So there won't be any issues when we enforce trusted types with the browser blocking any calls. And a word of warning here too, trusted types reports tend to be noisy just because we don't control the user-defined browser environment. There might be extensions or even malware running on the user's setup, so we'll spend some time sifting through the reports and find the actionable ones that actually do matter and that we need to actually go fix them. Finally, once we're done iterating steps 2 and 3, we can switch to enforcing mode and be sure that our service is protected against DOM XSS. And we do have a published blog post about this if you wanted to read in more detail. We went through a journey of refactoring AppSheet, which is one of Google's products, to make it trusted types compatible. You can either scan this QR code or go to bughunters.google.com, where we have a lot of different security blogs. So now let's dive into how we can do steps 2 and 3 and investigate runtime violations. As we mentioned earlier, there's a reporting mechanism that posts a JSON of the violation to our backend. We can take a deeper look at what that data is being sent in the network tab of Chrome DevTools and how this will help with our debugging. So these are the fields that will help with finding where in our code the dangerous call happens. So document URI is the first one that sticks out. This is the actual page or the endpoint where the violation happens. This is useful for reproducing what user interaction creates a violation. And then the second bit of information that's helpful too is the source file. This will tell you which JS file is responsible for the trusted types violation, and the line and column numbers should help you find the exact call site. One caveat here is that the source file might be empty if the violation comes from a script tag that's included in the initial HTML response, or we also encounter Chrome extension as a source file for noisy reports, and we usually feel free to discard them because that's not in scope for our project. We can also look at the script sample, which carries 2 bits of information. The first one being the sink itself. This will tell you which dangerous DOM API was used. And on the right side, you'll see the value of the string that was passed into the sink. This is usually truncated at 40 characters, but it should give you a good idea. So we've drawn up this methodology and mind map of what we actually do when investigating trusted types. So we look at the violation report first. What is the DOM string that was used? What is the string value? Is it user input? Is it code? Is it a hard-coded string we can easily find with some code search tools? If you haven't found it yet, you can do some runtime analysis. For this, you have to make sure that you have the header in your local setup. You can use Chrome local header overrides or mod header or any other Chrome extension that helps you do this. You have to browse through the app in order to trigger the violation. And once you do trigger it, Chrome debugger will help you kind of trace through where it came from. The only caveat here is that you might end up in a minified JS file, in which case we recommend to just look for hints as to where it might have been minified from. It is hard, but you do develop some intuition over time.
Thanks, Jen. So now that we've talked about how to investigate violations, we can talk about some common patterns that we run into and how to refactor them. So first, a common case that comes up is when we have some strings that might be user controlled, in which case we can escape the input to make sure it is safe before it's placed on the page. In this example, we can see the dangerous parts in this image tag are essentially disabled because the special characters will no longer be interpreted as code, but as text. If the user input is mostly meant to be text and not as markup, then we're okay to use this technique since it won't break functionality. And if there is an attempt at cross-site scripting, then we will be protected against it. Even better, though, is trying to use safer alternative DOM APIs. In this example, text content is sufficient for our intended use case and is both safer and actually better for performance. In the case where you have constant values inline in your code, you can transform these into trusted types with safe values, which can take a template literal or various other formats. Or if you'd rather not use safe values, you can also write an inline policy that blesses this constant value. However, not all code is easily refactorable. In cases where the dangerous logic being used is too complex to be switched onto a safe-free API and is not a constant or a value following some regular pattern, legacy conversions can come in handy. The idea behind legacy conversions is that rather than holding up shipping trusted types or other protections for the entire code base because of this one location, we can make a note to return to it later. And while this might not be completely safe, since this code was already running in production, this isn't much worse than what was there before. And there will be a lot of benefits to the other locations that we can't find right now that we are unblocking. And using a function to mark these locations is useful because with modern development tools, such as right-clicking in VS Code, you can keep track of these locations and make sure to come back to them later to either replace them or refactor them. One thing to keep in mind is that when we're converting strings into safe types, we want to do it as close to the source as possible so we can easily reason about whether the sources are safe or not. This is because the value can be modified and passed through functions that can potentially alter the values. This applies to our legacy conversions that we just talked about, as well as other conversion methods such as reviewed conversions. And these are a way to mark that we've checked the location and we're sure that usage of the string is safe. Here we can see that we leave a bit of justification on why this is the case so that we don't lose context when we return to this code location later. We always want to first try the other methods to construct safe values first. But when adopting an existing code base to be compatible with trusted types, sometimes it's the path of least friction rather than refactoring a lot of legacy logic. And when it's obviously visibly safe, there's not much issue there. So now that we've talked about how to refactor our own code, what can we do about code that isn't part of our application logic?
Yeah, and this is the part that's not as straightforward. How do we fix violations when they happen in third-party dependencies that we don't have control over? The ideal path that we hope for is that we patch upstream repositories, upgrade our library, that's a clean integration with our product, and we help make the JS ecosystem better if somebody else is using the same library to enforce trusted types. But unfortunately, this is not always the case, and this is actually most of the time not the case. Often our pull requests are pending for approval for a long time. We need to convince maintainers and have a discussion about what trusted types is and how our patch fits in with the overall repo. And in other cases, we can have dependencies that are multiple levels deep. So even if you do submit the patch, you have to then go back to everyone else on the chain and upgrade their dependencies, which is not the easiest thing. Our solution to this so far has been to fork the repository, set up a private copy, apply our patch, and generate the minified JS file and hook that into our product to avoid the violation. As you can see, this is just very tedious. And while it works, it's not sustainable in the long run since it adds maintenance costs. If the library is updated, we would need to do additional work to make sure our patch still works. So an alternative to this that we've come up with is the default policy. The default keyword is used to define a trusted types policy that will be, as the name suggests, applied by default. So this allows you to define some fallback behavior. In this code snippet here, we see a default policy defined specifically for trusted HTMLs, and we just apply a blanket sanitizer from DOM Purify to prevent XSS. And this way, anytime a trusted HTML violation happens on your site, the browser will call the default policy, which applies the sanitization. Another use of the default policy we found really useful is to allow certain static patterns. jQuery is one that comes up all the time during our rollouts, where jQuery will actually use inner HTML under the hood, especially when first creating elements, as you see here, like a link or a text area. Since we can't fix this in jQuery, we can write a default policy to allow only these inputs since we know they're safe and therefore unblocking our trusted types adoption. One important caveat here is that since the default policy is applied to all violations of a given type, it might silence behavior, so you should use it carefully. But the spec offers a nice solution to this. If the default policy returns null, the browser proceeds to generate the violation. The biggest advantage of this default policy approach is the reduction in the refactoring of multiple DOMs and call sites. This means reduced workload on having to manually review and refactor call sites. But this also happens to be our biggest disadvantage, however. We always say that even though trusted types is only supported on Chromium browsers, Chromium-based browsers now, the refactoring approach that we promote promotes safer coding patterns across the code base. Therefore, all of your users reap the benefits of trusted types. But this is not true when you only use a default policy, as it only is applied at runtime on a Chrome browser. And there's other risks to this, like sanitizer configuration is a big area of research. We gave you an example of a blanket sanitizer, but in reality, you would probably have to add more specific attributes that might allow for an attacker to bypass the sanitizer. So while we do think it works, it's not the most recommended approach. Cool. That was the end of our talk, and here's some conclusions. If we are out of time, I can...
We are
Yeah.
out. Yes, the next team is getting
Cool.
ready
This
to
is just
come
a
in.
summary of what we talked about. Thank you for coming to our talk, and we're happy to answer questions.